Quantum computing has the promise to solve a lot of problems that are critical to mankind, including the development of new materials, new drugs, and solve a whole bunch of problems that were considered unsolvable until now. It's a very big challenge to scale quantum computers to the useful level. You need at least 1 million physical qubits with today's technology to make them work, and it's a tremendous engineering challenge. The challenge to create a useful quantum computer is scale. You need 1 million qubits to make it work. Imagine that you can get it to work with only 100,000 physical qubits. This is something that is a huge enabler for the industry. Our vision is to help make optical quantum computers faster and more affordable. Quantum Pulse developed a technology that can integrate with any photonic quantum computer and make it 10 times smaller or 10 times less expensive, or in some case 10 times faster than other technologies. Quantum Pulse is delivering this breakthrough through a change in something called the directional coupler. Directional coupler is this optical junction where two qubits can interact in the photonic circuit. Think about it as the transistor of optical computing. So how do we make it better? We first have to understand the problem, and the problem comes with inaccuracy in manufacturing. Even a change in 1 nanometer in the layout of the photonic circuit compared to the intended design introduces problems that compound with the calculation process and makes it more prone to errors.
The inspiration came from the MRI field of research and technologies, and I understood 10 years ago how to take this concept of composite pulse or composite segmentation into integrated photonics. Instead of one waveguide, uniform waveguide, one segment of uniform waveguides, you can take several segments in the right order, with the right strength, with the right geometries, and then cancel out the errors of the gates. We can take several segments, like the several pulses, that will do destructive interference of their errors in the end, and then making a gate, a physical gate, quantum gate, that it's much more resilient to fabrication error.
Quantum computers are actually very, very delicate objects. So the biggest problem is noise. So therefore you have to fix it, because you need to make billions and billions of calculations. So you need to reduce the noise. The question for us was, is it possible to reduce the physical error of the device below that threshold? And after that, then you can also save qubits. Most of the applications that people think about, analyzing massive amount of data and very fast, they all require fault-tolerant quantum computation. You can reduce the noise using quantum error correcting codes only if you are below a certain threshold. Namely, your physical error should be below a certain number. There is a theoretical model and simulations, but then we proved it in laboratory. We actually fabricated the new designs, compared them to the other designs, and saw that we reduced the error, or in another language, we increased the fidelity of the gate of the quantum device. What our patent can do is can take the error, reduce the physical error, and bring it below the threshold. That's a huge step.
Quantum Pulse addresses the error, the possible errors on individual device of a quantum computer, photonic quantum computer. So what it does, it actually reduces the error fundamentally on every single device, every single qubit in a photonic quantum computer. For every logical qubit, you'll need 10 physical qubits. But if you are able to reduce the error, then it means now that the number, and you are now well below the threshold that is necessary. The lower you make it, the more you save on the number of devices that are needed to make error correction. And of course the computation time. If the error is smaller, computation time becomes shorter, which is also a big factor. The technology of quantum pulse is real. It has been proven in the lab. You can reduce the error in the splitting ratio between the two channels, and you can reduce the error in the phase. Technology is real. To take it up now and bring it up to a full-scale quantum computer, this should be considered as enabling technology. Without this, it's going to be extremely difficult to make a quantum computer.
The net effect of quantum pulse technology is that the same fabrication capability will provide a much higher fidelity in the quantum computation because of this new design of the directional coupler. Quantum pulse makes its technology available for licensing to anyone that is building an optical quantum computer. Our technology is universal, patent protected, and has the ability to integrate with any design. The only thing that we impact is the directional coupler that is in the heart of every photonic computer. Quantum pulse technology levels the playing field. It allows new entrants to enter this very competitive market of optical quantum computers, making the problem of getting to the critical mass required for useful algorithms 10 times easier, or making the bar 10 times lower. After making quantum computers work, we still have to deal with the challenge of the prohibitive cost of the solution. These things may cost up to $1 billion a piece, and by our ability to reduce the complexity of those machines by an order of magnitude, you can save up to $900 million out of this $1 billion, making them proliferate faster and deliver faster on the promise to actually help humanity at large.